In this video, I'm going to briefly discuss something called the Heisenberg uncertainty principle. Heisenberg basically discovered this through the fact that he was investigating a form of quantum mechanics in terms of matrices. He called it matrix mechanics. And it turns out that multiplication in matrix multiplied does not commute in general. It can, but it doesn't have to. And so we've already discussed commutators where we had a product of two operators which did not commute. And that example was the position of the momentum operator. So we evaluated that commutator and we saw that it was minus h bar over I, not 0. If the operators commute, then the commutator is going to be 0. Well, it turns out that the uncertainty in the position and the uncertainty in the momentum, the product of those two is greater than or equal to 1/2 of the absolute value of the commutator. Since the commutator's absolute value is h bar, this is what you'll see in textbooks. Okay, now so what that means is you can more or less derive your own Heisenberg uncertainty principle for any two operators. Just evaluate the commutator, take the absolute value, multiply it by 1/2, and you'll have a different Heisenberg uncertainty principle. And the other example you're going to see is for angular momentum. Turns out we cannot know the quantum numbers for angular momentum for the total angular momentum, L, and we can know one of the components, for example, m sub L, but we can't know the orientation with respect to other directions. All right, so we're going to just discuss an example or two. The thing I want to point out is this delta is not an experimental error. It's actually an inherent uncertainty in the system. That's to say, if you have a wave function and you want to know what the position range is for that system and the momentum range for that system, it turns out that this product has to be greater than or equal to h bar of 2. There's no way to do it otherwise. So let's discuss two rather extreme examples. The free particle we've already looked at has a fixed wavelength, the de Broglie wavelength. And so the momentum of the free particle, remember, is kh bar, where k is a constant. Well, that means the wave function, when we look at it, it has probability, which is going to be the square of this wave, everywhere in space, which means delta x is infinite. Okay? So we can't know the exact momentum without losing complete track of where the particle is. So the other extreme is to look at a particle and find out its exact position. Well, you can't do that. You can't make delta x equal 0, but you can get it's very, very small. It turns out that when you do that, the uncertainty in the momentum of the particle becomes crazy. So you can think of this wave function as being a combination of a series of waves, all of their own momentum. And so the only way to actually get a wave function that's this localized to one position is to have more or less an infinitely wide spread of momenta. That is to say, waves of all wavelengths combining so that you only get interference in one area. Okay, so what is the formula for delta x? So delta x is the standard deviation. So how do we calculate standard deviation? Well, in statistics, you know, you take the mean and then subtract from the mean, and then you square it, and then you add it up, and then you take the square root and all that. So when you do that with operators and expectation values, so it turns out delta x is going to be the square root, right? And it turns out the sums of the squares of the deviations from the means is going to be this. So x bracket is the average or expectation value of x. It's the average. This is the mean. All right, and so in deriving the standard deviation of x, it turns out the other thing you need to do is x squared Okay, so basically, the only way you're going to get this to be 0 is if all the deviations are 0. That is to say you have no deviation at all. So this can average to 0 in principle if you have the same number of positive deviations from the mean as negative deviations to the mean, then the average will be 0. So, but the deviations squared are all positive numbers. That's the whole reason we square them. And so this must be a positive number. All right, and so let's look at the particle in a box, or particle on a line. And so it turns out that when we calculate the expectation value, which remember, it's going to be the integral of the complex conjugate of the wave function, then the operator x, which is just multiplied by x, and then the wave function again, and then since it is particle on a line, dx, and since it's particle on a line, the integration range is 0 to L, because psi is 0 outside the interval, so the expectation value outside 0 to L is going to be 0. All right, so it turns out that when we look at the average position of the particle in the box, it's L over 2. And so, because it's a symmetric distribution about the middle of the box, which is L over 2. Now, if we take all the x squareds and average them, then we're going to get a completely different animal. That's a rather more complicated integral, so I'm going to look that up. But first of all, just define it. So the x squared expectation value is going to be the same integral, but with x squared in the middle. Which is a different integral, which is a different value. Note that this thing is going to get squared, so when we plug it into delta x, it's going to be L squared over 4, and it's going to be subtracted from whatever this integral is. So let's see what it is. It is L squared times 1/3 minus 1 over 2 pi squared n squared. So it depends actually on n squared. Now you can see as n squared approaches infinity, the second term becomes closer and closer to 0. So we'll have L squared over 3, and that'll be subtracting the L squared over 4, so that should be, what, L squared over 12. And so as we go up in the energy levels of the particle box, the uncertainty in x approaches whatever the square root of, it's going to be L over square root 12. Okay, but for the very low lying wave function where this is n equals 1, it's going to be 1/3 minus 1 over 2 pi squared. And that'll be a different number. You can actually enter these numbers in your calculator. All right, so similarly, we can do the delta px, and that turns out to be 0. And then delta px squared, sorry, not delta px, that's impossible. Px expectation value is equal to 0. And all right, well, that's going to just be, since this is a kinetic energy only system, p squared divided by 2m is the total energy of the system. So I can take the energy of the particle in the box and multiply it by 2m, and I'll get p squared. So I'm going to cheat and just use energy levels for particle in the box. 2m, all right, times n squared h bar squared over 2m L squared. Okay, well, looky there. 2m divided by 2m. So it's going to be n squared h bar squared over L squared. Let me check and make sure that's correct. Hey, how about that? Times pi squared. Ah, forgot my pi. Okay. So if we plug that in, we're going to get delta p. So we take that minus this squared and take the square root. And so when we do that, first of all, we'll look at the units of delta x. They're going to be units of length. When we look at the units of delta p, they're going to be units of momentum. So you can analyze the units here. And when you calculate delta p, it should be newtons, or the analogous things with kilograms, meters, and seconds squared. But it turns out that delta x, delta px, in terms of h bar, all the numbers times h bar, is going to be 0.568 h bar if n equals 1. If n equals 2, it's larger. N equals 3, it keeps getting larger and larger. And so is this larger than 1/2? Well, 1/2 is 0.5, so this is greater than h bar over 2. All right, well, that's it for the Heisenberg uncertainty principle, illustrated with some expectation values using the particle in box wave function.